contains number of closely hello. Actually, I made a fresh connection. Now the sound is clear or not? Hello. Hello. Now is it clear? Everything is clear?
Yes, sir. Now it is clear.
Okay. Okay. So, during the such type of transition, for example, in gaseous or vapor phase, the spectrum contains number of closely spaced lines consisting what is called a band spectrum. So that means here number of closely spaced lines you will find. So that's why this type of spectrum. So that is called band spectrum. However, in solution phase, the absorbing species are surrounded by solvent molecules and undergo constant collision with them. So these collisions and the interactions among the observing species, the solvent molecules cause energies in the states around quantum states to spread out. As a consequence, the sample absorbs photons spread over the range of wavelength, thereby the spectrum acquires the shape of smooth and continuous absorption peak in the solution phase. So a typical UV visible spectrum of the solution phase is shown in this figure. So this is a UV visible spectrum. So this is in vapor phase. You can see in vapor phase sharp lines are there. Sharp lines means closely spaced electronic uh, uh, band spectrums are there. But in case of solution phase, a broad spectrum is there. So why this type of so broad spectrum you will observe? Because in case of solution phase, the solution molecules, the samples are also surrounded by solution molecules, so that will give a broad spectrum or continuous. So this type of spectrum are called continuous spectrum. But in case of gaseous molecules in vapor phase, in case of gaseous molecules in vapor phase, you will find sharp lines or sharp peaks are there. So this is the UV visible spectrum of gaseous molecules or in vapor phase, and this is the UV visible spectrum of molecules in solution phase. Now coming to the characteristics of UV visible spectrum. Now in order to obtain UV visible spectrum, the sample is ideally irradiated with the electromagnetic radiation varied over a range of wavelength. A monochromatic radiation, that is a radiation of single wavelength, is employed at a time. This process is called scanning. That means to get for the analysis of the sample, the electromagnetic radiation of the UV visible range, that means around 200 nanometer to 800 nanometer. So there will be complete scan will be there. For every scan, for every step, there will be a particular wavelength or monochromatic wavelength. That means initially electromagnetic radiation of 200 nanometer will pass through the sample. After that 200.5, then 201, then 201.5, then 202. So gradually from 200 to 200, from 200 nanometer to 800 nanometer, so different wavelength will be scanned throughout the sample. But for every time, a single monochromatic wavelength is employed at a particular time. Now, the amount of radiation observed at each wavelength is measured and plotted against the wavelength to obtain the spectrum. So, thus, a typical UV visible spectrum is, is a plot of wavelength or frequency versus intensity of absorption. So, the electromagnetic radiation will be varied from 200 nanometer to 800 nanometer. Now, according to the characteristics of the sample will observe electromagnetic radiation of particular wavelength. So that will not absorb the electromagnetic radiation of the remaining wavelength. So at which particular wavelength the sample will absorb the electromagnetic radiation, in that for that electromagnetic for that particular wavelength the observance will increase. So that's why we will get the spectra. So in the figure 2.1b, the abscissa x-axis indicate the wavelength of the wavelength observed, therefore that is marked in the wavelength, though sometimes the frequency may be used. So so in this figure you can see the x-axis, you can see for x-axis, that is the wavelength ranges from 0 to 800 nanometer. So according to the nature of the sample, here you can see the sample observed initially at some 243 nanometer. After that again that will observe around 247 nanometer, then that will absorb around 248 nanometer, then that will absorb around 253 nanometer, then that will absorb around 258 nanometer. So that is according to the nature of the sample that will absorb electromagnetic radiation of particular wavelength. So at that position the observance will increase, so we will get the spectra. So in this figure, the x-axis indicate wavelength observed, and therefore that is marked in wavelength, though sometimes frequency may also be used. So in some graph you can find frequency, but most of the curve you will find wavelength versus observance. Wavelength will be in the x-axis and observance will be in the y-axis. Now, the y-axis, other hand, represent the intensity of absorption, that is generally represented in terms of observance. The UV spectra of the substance are characterized by two major parameters, that is namely position of the maximum of the absorption band, that is called a lambda max, and the intensity of the band. The lambda max refers to wavelength of the most absorbed radiation and is measured in the difference in the electronic energy levels involved in the transition, and the intensity other hand indicate the probability of the transition. So that means if you will see this graph, so this one is lambda max, that means for particular this wavelength means the wavelength is around 208 nanometer. So at 208 nanometer, that means when electromagnetic radiation of 208 nanometer will pass through the sample, according to the characteristics of the sample will absorb maximum electromagnetic radiations of 208 nanometers. So that's why in this case we will get lambda max here. So this is the lambda max value. So the lambda max value is this one corresponds to lambda max value because at this wavelength the sample absorb the maximum electromagnetic radiation. That's why its absorbance will be maximum, and this wavelength is called lambda max. Now, the characteristics of the UV visible spectrum depend on the structure and the concentration of the absorbing species in the solution. First one, we will discuss what is absorbing species. The UV visible spectra arises due to electronic transition in the absorbing species. The electronic transition do not occur in all species. When the radiation of UV region is passed through the sample, generally three types of species show the these are organic species, maybe inorganic species, or maybe complexes formed by charge transport. So this is charge transport. So first one is organic species. So the molecular absorption in the UV visible region depend on the electronic structure of the molecule. So, so first one we are discussing the UV visible spectra of organic molecules. So for organic molecules, the molecular absorption in the UV visible region depend on the electronic structure of the molecules. The wavelength of the radiation absorbed by an organic molecule is determined by the difference in energy between the ground state and the various excited electronic state of the molecules. So for this reason, now we will discuss what are the different energy levels in an organic molecule. So in an organic molecule, what are the different energy level and what is the ground state energy level and what are the different excited state energy levels. So bonding in organic molecule, that the constituent atoms are bonded. We know that in organic molecules, the constituent atoms are bonded through pi and sigma bonds. In addition to this, the molecule may contain some non-bonding electrons or lone pair of electrons in the atoms like nitrogen, oxygen, sulfur, halogens, etc. So if the organic molecule contains this type of heteroatoms like nitrogen, oxygen, sulfur and halogen atoms, then the molecule will contains some lone pair of electrons associated with these atoms, nitrogen, oxygen, sulfur or halogen, etc. So there are a number of transitions possible involving the bonding and the non-bonding electrons. So the generalized molecular orbital energy level diagram and the possible transition for organic compound is given in this figure. So in this figure, you can see in an organic molecules, what are the generalized electronic energy levels. So the first one is sigma bonding molecular orbital. Sigma bonding molecular orbital. We know that the sigma bonding between the two atoms is very strong and that is very stable. So that's why it is having least energy. So having lowest energy state. And after that, pi bonding molecular orbital. So which comes with the next energy level, next higher energy level, and after that n, that is called non-bonding energy levels. So that means if the organic molecules contains heteroatoms like nitrogen, oxygen, sulfur or halogens, then some lone pair of electrons are associated with these nitrogen, oxygen, sulfur or halogen atoms. So these lone pair of electrons will present in non-bonding molecular orbital because they will not participate in the because the lone pairs will not participate in bond formation. And after that, the next energy level is pi star, that is antibonding molecular orbital, and the next one is sigma star, that is antibonding molecular orbital. So these are the different electronic energy levels present in organic molecules. So these are the generalized molecular organic energy levels. And now we'll discuss what are the possible electronic transition arises when electromagnetic radiations of UV visible range will pass through the sample where the molecule contains these different energy levels. Now, as per rule, the transition occur when the highest occupied molecular orbital, that is called HOMO, to the lowest unoccupied molecular orbital, that is called LUMO, in a molecule. In most of the organic compounds, the bonding and sometimes non-bonding orbitals are also filled and the antibonding orbitals are empty. So generally, you can see the antibonding orbitals are having higher energy state. So sometimes in most of the molecules, these antibonding orbitals or these antibonding energy levels are empty, and this bonding sigma pi bonding and non-bonding energy levels are occupied. Out of the six possible transitions indicated in the figure, only two of the lowest energy levels. So here you can see, so these are the six possible transition. So the first possible transition is transition of electron from sigma bonding molecular orbital to pi antibonding molecular orbital. Sigma bonding sigma to pi star. And the second possible transition sigma to sigma star. The third possible transition pi to sigma star. Then pi to pi star, then n to sigma star, then n to pi star. So these are the six possible electronic transitions that may take place when the sample will be irradiated through electromagnetic radiations of different wavelength. So out of the six possible transitions indicated in the figure, only two of the lowest energy levels can be achieved by energy available in the 200 to 800 nanometer region. Let us learn about these two in the following paragraph. So here we will discuss the two lowest possible energy levels. So these are the two lowest possible energy transition, that is n to pi star and pi to pi star. So pi to pi star, and the next one is N2 pi star. So these transitions are observed in the molecule containing pi electron. So for these transitions, the organic molecule must contain pi electron. That means the organic molecule must contain pi bond and occur at a wavelength approaching near the ultraviolet region. So the hydrocarbons containing double bonds or triple bonds are typically examples of this type of transition. For example, you can see ethylene. Ethylene, that is ethene, that observed at 170 nanometer, and the conjugation of unsaturation further increases the so first one is ethene CH2 double bond CH2. So here you can see one pi bond is there. So as pi bond is there, so this n to pi this pi to pi star transition is possible here because the molecule contains pi bond. And
Sir, your voice is not coming.
hello, hello,
हेलो
hello,
आवाज आ रही है सर
okay. So here this the molecule contains one pi bond, so that's why pi to pi star transition is possible for these molecules. So initially we have also discussed that hydrocarbon containing double bond or triple bonds are typically examples which deals with this type of pi to pi star transition. And you can see for so here in a typical example, ethylene, so this molecule will absorb around 170 nanometer. That means when electromagnetic radiation of wavelength 170 nanometer will pass through the sample, so that will causes the transition, the electronic transition from pi to pi star energy level. And again, the conjugation of unsaturation. So here only one double bond is there. And another example is bute 1,3 diene. So this one is bute 1,3 diene. CH2 double bond CH single bond CH double bond CH2. So this is bute 1,3 diene. You can see for bute for the first molecule only one double bond is there. For the ethylene molecule only one double bond is there. But for the bute 1,3 diene two double bonds are there, and the two double bonds are in conjugation with one another. Another aromatic compound, that is naphthalene. So the lambda max value increases to 300 nanometer. And similarly for anthracene, again the lambda max value increases to 360 nanometer. So that means if the conjugation will gradually increases, the value of the lambda max will also increases. That means the molecule will absorb at longer wavelength. Now coming to another type of possible transition in organic molecules, that is called N to pi star transition. So these transitions are observed in the molecules containing lone pair or non-bonding electrons. We have already discussed that if the molecule contains some heteroatoms like nitrogen, oxygen, halogen or sulfur, then the heteroatoms will associated with lone pair of electrons or non-bonding electrons. That means these electrons will not participate in the pi or sigma bond formation. So this type of transitions are possible if the molecule contains heteroatoms like nitrogen, sulfur, oxygen or halogen. In such transition, one of the non-bonding electrons may be excited into empty pi star orbital. So here non-bonding, so the non-bonding electrons will present in this energy level, so they may excited into empty pi star orbital, or they may excited into empty sigma star orbital, but this is of higher energy, that is not possible within the UV visible range, but this one will possible in the UV visible range. So the energy required for these transitions are lower than that for pi to pi star transitions, and results the absorption in the ultraviolet and visible region, and the presence of atoms or groups containing N electrons can cause remarkable change in the spectrum. Thus, nitrogen, sulfur, or halogen or oxygen tends to move the absorption band or the absorption to higher wavelength. So, if this type of heteroatoms will present, so that means if non-bonding electrons will be there, then the molecule will absorb at still longer wavelength than that of the pi to pi star transition. Now, the second case is now another factor that the pi to pi star transitions are generally intense, although that will takes place at shorter wavelength. But the N to pi star transitions are takes place at longer wavelength, but these are weak. But pi to pi star transitions are takes place at shorter wavelength. These are intense. While the N to pi star transitions occur at longer wavelength, but these are weak. For example, if you consider acetone molecule, so acetone molecule, that is CH3 C double bond O. For acetone molecule, that is CH3 C double bond O. So here pi bond is there. As pi bond is there, that means pi electrons will be there. There will be possible pi to pi star transition. Apart from that, the oxygen atom contains two lone pair of electron. As the oxygen atom contains two lone pair of electron or non-bonding electron, that means n electrons, then n to pi star transition is also possible. So in case of acetone, the pi to pi star transition takes place at 195 nanometer, that is not within the UV visible region, but but the N to pi star transitions occurs at 274 nanometer, that occurs within the visible, within the UV and visible region. But here the pi to pi star transition will be intense, and N to pi star transition that is occurring at 274 nanometer, that will give low intense or weak peak. But pi to pi star transition will give intense peak. So here this is the UV visible spectrum, that is particular UV spectrum, because here there is no chance of transition within the visible range. So here only we are showing the UV spectrum. So the UV spectrum of acetone, that is showing pi to pi star transition and N to pi star transition. The first one is occurring at shorter wavelength around when so here the lambda max is 195 nanometer. So that is due to pi to pi star transition, and this one is intense. But the N to pi star transition occur at longer wavelength around here the lambda max is 274, but that is less intense. Its intensity is low, but its intensity is high. Thus, only those molecules are likely to absorb light in the 200 to 800 nanometer region, which contains pi electrons and may also have may also have atoms with non-bonding electrons. Such group that will absorb light in the UV visible region, these are referred to as chromophores. Again, so this is the definition of chromophore. So only those molecules are likely to absorb light within 200 to 800 nanometer. That means within the UV visible region, which contains, that means which organic molecule will absorb within this region? The organic molecule which contains pi electron. That means if there will be pi bond, and also the organic, if the organic molecule will contains non-bonding electron, that means if there will be nitrogen, oxygen, sulfur or halogen atom, then then there is a possibility that the organic molecule will absorb electromagnetic radiation within 200 to 800 nanometer, and these molecules are called as chromophores. The chromophore in Greek, that means color bearing. However, the term chromophore is now not limited to color only, but that is used generally a way graph which are responsible for causing absorption of electromagnetic radiation between about 175 nanometer to 800 nanometer. So here it is a absorption characteristics of some common chromophoric group. So here if one carbon carbon double bond is there, so this is the chromophoric group, and the transition possible within the molecule is pi to pi star transition. Here the lambda max value is 177, and if carbon carbon triple bond is there, the lambda max value is 178, and the possible transition is also pi to pi star transition. And if carbon double bond O is there, then non-bonding electron is also there, and also a pi electron is there. So two types of transitions are possible, that is N to pi star and also N to sigma star transition. And similarly, N to pi star, one is N to pi star and another one is pi to pi star transition. And similarly, for acetaldehyde, so these two types of transitions are possible. And this is for acetone, for carboxylic acid. If carboxylic acid group is there, its lambda max value increases, and the possible transition, this one is the possible transition. And this is for amide group, acid amide group. So here this is the possible transition N to pi star. So as the molecules contains heteroatoms, so these type of transitions are possible. Now coming to inorganic species. A large number of inorganic salts containing atoms with electrons in the d orbitals give weak absorption bands in the visible range. The ions and the complexes of the element of the first two transition series belonging to this group, and these are colored. And the color of these species are due to absorption are due to transition of electrons among the d orbitals. So the complex formation of these ions with solvent molecules or with other ligand leads the degeneracy of the 5d orbitals. So that means when the transition atom will undergo complex formation or molecule will undergo formation of complex or molecules, when they will associated with different ligands, then the degeneracy of the d orbital will be removed. Degeneracy means initially when the transition metals will be in the isolated state. Isolated state means only in the atomic or ionic state. Then the 5d orbitals dxy, dyz, dzx, and dx square minus y square and dz square, the 5d orbitals will be having same energy, so that's why that is called a degeneracy. But when they will form complexes or molecules when associated with the ligand, their degeneracy will be removed. So for example, if that will form octahedral complex, then dxy, dyz and dzx orbital having lower energy, that is called a T2g, and dx square minus y square and dz square orbital having higher energy, that is called eg. So the five d orbitals which are initially degenerate orbital, now they will split into two different energy levels. So now if electromagnetic radiation of the UV visible range will pass or will fall on the sample, then there is a possibility of transition of electron from the T2G to EG set. So that will give rise to absorption spectra. As a consequence of this split into groups having different energies, the electronic transition from the lower energy d orbital to higher energy d orbital are responsible for the observed color. So these transitions are called DD transitions. And the blue color of the aqueous solution of copper sulfate and violet color of the potassium permanganate solution are due to some examples of this type. And similarly, exactly in the similar way, the ions of lanthanides and actinides are also colored. However, these involve due to FF transition. Just like DD transition, in case of transition metal complexes. So similarly, for the molecules or the complexes of lanthanides and actinides, there is also possible of FF transition. So the nature of the spectrum in case of all the ions is different because the F electrons are relatively less affected by external influence due to by shielding by the occupied orbitals of higher quantum number. So the ions absorb radiation in the ultraviolet and visible radiation in narrow bands, and the representative visible spectra of transitional metal complexes and inner transitional metal complexes are given below. So these are the electronic transition spectra in the UV visible region for transitional metal or for transitional metal complexes, and these are for inner transitional metal complexes or metal ions. So here narrow bands are there, but in case of transitional metal ions, broad bands are there. Now coming to another type of UV visible transition, that is called charge transform complex. You can see a given compound that is transparent in the UV region starts absorbing after interacting with another species. This happens if one of the species has an electron donor group, electron acceptor group. Suppose one of the species will having electron donor group, that means that is having so that if the species will be electron rich species, so that can have the possibility to donate electron. And similarly, another species which is electron deficient species, so that is the species has an acceptor group. When the two species are bind to each other, the resulting species is intensely colored. This is due to formation of a complex between the two species, and such complex is called charge transfer complex. For example, the blood red color of the complex ion Thiocyanato iron, thiocyanato iron 3 ion. So this is thiocyanato iron 3 ion. So this is having blood red color due to the formation of charge transfer complex. So here this is the UV visible spectra of so the spectra of the charge transfer complex. So that will the lambda max will fall within the visible range. So that's why the color of this complex is red, blood red color. The radiation absorbed by this complex or product cause transfer of an electron from the orbital in the donor to orbital in the acceptor. So when donor is associated with acceptor, so that will form the complex. And when electromagnetic radiation of UV visible range will irradiated with the sample, then the radiation absorbed by this product or complex cause the transfer of an electron from an orbital of the donor atom to orbital of the acceptor atom. This has been schematically shown in figure 2.6. So you can see, so this is 2.6. So this is the energy levels of donor atoms. This is highest occupied molecular orbital energy level HOMO, and this is lowest unoccupied molecular orbital energy level LUMO. So this is for the donor state. And now when the donor is associated with the acceptor state, so for acceptor state, this is HOMO and this is LUMO. Now when the donor and acceptor will combine one another to form the complex, so there is a large chance of transfer of electrons from the HOMO of the donor to LUMO of the acceptor, which is having very less energy transition. So that will fall within the visible range. So in the figure 2.6, the transition in the donor and the acceptor species individually are high energy. So if there will for the transition, for the electronic transition of donor individually need high energy. Similarly, for the electronic transition for the acceptor individually also need high energy. But when the donor and acceptor combined with one another to form the complex, so for the electronic transition of HOMO of the donor and LUMO of the acceptor require comparatively very less energy. So that's why that is called charge transfer complex. So a large number of chelating agents are used for the spot test. The intense color of the such metal chelates is due to the charge transfer transition. They are simply involved in the movement of electrons from the metal ion to the ligand and vice versa. Now the complex between the thiocyanato, so this one, the thiocyan, so in the above discussed example, that is thiocyanato iron 3 complex. So here the thiocyanato is SCN minus and iron 3 complex Fe3 plus. The absorption of photons transfer an electron from the thiocyanate ion to the Fe3 plus ion. Besides the metal ion, the non-metals and their ions are also form colored substance which produce characteristic spectra. For example, alkaloid brucine react with nitrate ion in the concentrated sulfuric acid to form a red complex, to form a red compound which quickly turns yellow color. Now coming to the principle of UV visible spectrometry. In a typical absorption spectral measurement, a monochromatic radiation is made to fall on the sample taken in a suitable container that is called cuvette. So again, for a typical absorption spectral measurement, so that means if you want to do the UV visible spectrum of any sample, you have to put the sample in solution phase inside a container, suitable container. That container is called cuvette. So in such a situation, a part of the radiation is reflected, a part of the radiation is absorbed, and also a part of the radiation is transmitted. Now the intensity of the original radiation, if the intensity of the original radiation passed through the cuvette containing the sample is P naught, so P naught equals to summation of intensity of the radiation reflected plus intensity of the radiation observed plus intensity of the radiation transmitted. That means P naught equals to PR plus PA plus PT. Now, the effect of radiation can be compensated by passing equal intensity of beams through the solution and through the solvent containing the same similar container and comparing the transmitted radiations. Then we can write the above equation as P naught equals to PA plus PT. So the intensity of the transmitted light is measured and it is found to depend on the thickness of the absorbing medium and the concentration besides the intensity of the incident radiation. And the dependence form the base the dependence form the basis of spectrometric determination, and that is given in terms of two fundamental laws. So one law is that is called Lambert's law, and another one is called Beer's law, which expresses the relationship between the light absorbed capacity of the sample and the thickness of the absorbing medium. So the first one is called Lambert's law, that that expresses the relationship between the light absorption capacity of the sample and thickness of the observing medium. And similarly, another law that is called Beer's law, which expresses the relationship between the light absorption capacity of the sample and its concentration. Now, the two law in its combined form, that is called Beer-Lambert's law. So here we will discuss the Lambert's law first. So the Lambert's law, the Lambert's law independently studied the decrease in intensity of the radiation when it passed through a substance and made the following observation. So the first observation, that is number one, the amount of monochromatic light absorbed by the substance is proportional to intensity of the incident light, that is the ratio of the intensity of the transmitted and the intensity and the again I am so repeating, the amount of monochromatic light absorbed by the substance is proportional to intensity of the incident light, that is the ratio of the intensity of the transmitted and incident light is constant. And the second, the intensity of the transmitted light decreases exponentially when when the thickness of the substance through which light is passing increases linearly. So that means if thickness will increases, then the intensity of the transmitted light will decreases exponentially. When thickness will increases linearly, the intensity of the transmitted light decreases exponentially. This observation is called a Lambert's law, and that can be translated into mathematical expression. So if questions will come, you have to write the Lambert's law from here. So you have to draw this figure. So this figure illustrate for the establishment of the establishing the Lambert's law. You can see, so this is the Lambert's law in this figure 2.7. So this is the absorbing medium and intensity of light before passing through the absorbing medium is P naught, and intensity of light after passing through the absorbing medium, that is P. If P naught represents, so you have to start the long question of Lambert's law from here. First you have to draw this figure, and after that you have to write. If P naught represents the radiant powered light after passing through a slab of thickness B, so this is a slab of thickness B. So here you can see the thickness of the slab is B. This is the thickness of the slab, that is B. Consider a small slab of thickness dx, then changes. Consider a small slab of thickness dx. So here within this thickness B, we have to consider a small slab of thickness dx. So here, so this is a small slab of thickness we are considering. Within this total slab, we are considering a small slab of thickness, small slab having thickness dx. Then change in power dpx is proportional to power of the incident light px multiplied by change in the thickness dx of the slab through which the light is passed. So here this is px is the incident light before passing this small slab, and px minus dpx is the intensity of light after passing through this small slab. Again, I am repeating, px is the intensity of the light before passing through the small slab, and px minus dpx is the intensity of the light after passing through the small slab. Now, the change in the intensity is dpx. So before passing through the small slab, the intensity was px, and after passing through the small slab, the intensity is px minus dpx. So the change in thickness, that is dpx. The change in intensity, that is dpx. Now here dpx is directly proportional to intensity of the incident light px into dx. According to this law, dpx is directly proportional to px into dx, or dpx equal to some constant minus k into px dx. Why minus is there? Because there is a decrease in intensity. Where k is the proportionality constant and negative sign indicate there is the radiant power decreases. That means there is a decrease in intensity. And this equation 2.1 can be rearranged to dpx by px equals to minus k dx. Now integrating this, now this is equation 2.2. Integrating this equation 2.2 within limit p naught to p, the intensity, and 0 to b, the, so now if you consider for the total change in intensity, so the total change in intensity will be p naught to p. P naught is the initial intensity and p is the final intensity, and similarly total change in thickness is 0 to b. Now integrating this above equation 2 from P naught to P and 0 to B. So the left hand side is the integration for the intensity. So the limit of the left hand side integration is P naught to P, and the limit of the right hand side integration is 0 to B. So we can write the integrating form of equation 2 like this: integration of dpx to px, integration of dpx by px from p naught to p equals to minus k into integration of dx from 0 to b. So solving this, you can write, so the LHS of this integration is integration of dx by x, that is ln x. Now putting the limit, you can write ln p by p naught equals to minus kb. This is equation 3. So the equation 3 is mathematical expression of the Lambert's law, and changing the equation into, so here this is the logarithm log p naught by p equals to k by 2.303 b. So that means when ln will changes into log, logarithm base 10, you have to multiply 2.303, and that 2.303 will come to the RHS, and that will be divided. So that is equals to, so here you can write log p by p naught equals to minus k by 2.303b, and if we change the logarithm, so that is log p naught by p, then the negative sign will be removed, so that is equals to k by 2.303b, and here k is one constant, 2.303 is a number, so constant by any number, that is gives another k dash into b. Note that the ratio p by p naught has been inverted to remove the negative sign, so that we have, so this is about the Laplace law. So this is one of those. Okay, so now we'll continue from the Beer's law. So initially we have discussed one law. So we have discussed the long question that was Lambert's law. Now we'll continue for Beer's law. So we will discuss the Beer's law. So now consider a monochromatic radiation beam of intensity Px. Consider a monochromatic radiation beam of intensity Px traversing any thickness of the solution of a single absorbing substance of concentration C, and if C changes by a small amount from dc to C plus dc, so that means initially the intensity of the monochromatic radiation is Px, that is traversing any thickness of the solution of a single absorbing substance. That means there should be single absorbing substance should be there, and the concentration of the absorbing substance should be C. And if the C changes by a small amount dc, that means initially the concentration of the absorbing substance was C, and if the concentration of the absorbing substance changes to C plus dc, then the change in transmitting power dpx is proportional to intensity of the incident radiation, that is, and dc, that is dpx is directly proportional to px into dc. So this is the statement of the Beer's law, and this is the mathematical expression of the statement. And and here we are converting the proportionality equation into equality equation. So then that will become dpx equals to some constant minus k, some constant minus k double dash into px into dc. Here k double dash is the proportionality constant, and a negative sign indicates that the radiant power decreases. That means the intensity decreases with absorption. So this equation can be rearranged to dpx by px equals to minus k double dash dc. On integrating in the similar way, just like in the Lambert's law, on integrating in the similar way, we can from limit p naught to p for intensity and 0 to c for concentration. So we can write ln p by p naught equals to minus k double dash c, or we can also write log p naught by p equals to k double dash by 2.3033. So this equation 2.7 is a mathematical expression of the Beer's law, and the Lambert's and Beer's law are in combined form. So this was the mathematical expression of Lambert's law, log p naught by p equals to k by 2.303b, and here this is the mathematical expression of the Beer's law. So in the combined form, the mathematical expression of the Lambert's Beer's law can be written as log p naught by p equals to abc, where a is the constant, that is the multiplication of k dash into k double dash, that is called absorptivity, or that is also called as extinction coefficient, whose value depends upon the unit concentration used and a function of the wavelength of the monochromatic light used. Now the concentration is generally expressed in terms of gram per decimeter cube, and the unit of B is generally expressed in centimeter. Therefore, it has a unit of gram per centimeter per decimeter, gram inverse, centimeter inverse, decimeter cube. However, if the concentration is expressed in moles per decimeter cube and B is centimeter, then it is called molar absorptivity or molar extension coefficient, and that is expressed as epsilon. It is having the unit centimeter inverse, mole inverse, decimeter cube, and the modifier expression for the Beer's-Lambert's law, that is log P naught by P equals to epsilon Bc, and here the term log P naught by P is called the observance, and that is represented by A. So A equals to log P naught by P. The expression for the Beer's-Lambert's law becomes, now the expression for the Beer's-Lambert's law becomes log P naught by P equals to A equals to FBC or epsilon BC. So the observance A is related to another important term, that is called a transmittance, which is defined as fraction of the incident radiation transmitted by the observing medium. That means transmittance T equals to P by P naught. Transmittance P equals to transmittance T equals to P by P naught, and is generally expressed as a percentage, and that is expressed as percentage of transmittance T, that is equals to P by P naught into 100. And the transmittant is so related to observance according to the equation A equals to minus log T. So here that is a numerical question. The molar absorptivity of a substance is 2 into 10 to the power 4 centimeter inverse mole inverse decimeter cube. Calculate the transmittance through a cuvette of path length 5 centimeter containing 2 into 10 to the power 6 moles per decimeter cube solution of the substance. Now, according to Beer's law, we can write A equals to epsilon Cb. So here the value of the epsilon is given, the value of C is given, and B means path length or the width of the cuvette is given, that is 5 centimeter. Now substituting all the values, we can get the value of A, and after that we can find A equals to log 1 by t. So the value of the log 1 by t is given. Now taking the anti-logarithm form, we can find out the value of t. Similarly, so here another numerical question that you have to solve. Now, deviation from Beer-Lambert's law. As per the Beer's law discussed above, there is a directly proportionality between the observance and concentration will be there. So if the solution will completely obey the Beer-Lambert's law, then the graph between the concentration and observance will be a straight line, just like B, graph B. But in the actual case, there will be positive or negative deviation. Positive deviation will give the graph A, and the negative deviation will give the graph C. So the upward curve, the upward curvature of the curve is known as positive deviation, and the downward curvature of the curve is known as negative deviation. So this type of positive or negative deviations will be there. The law does not hold good for all species under every condition. Many times, instead of a straight line, a curvature in the plot may be observed as shown in the figure. Now, why this type of positive or negative deviations are coming? Presence of electrolyte, the presence of small amount of colorless electrolytes which do not react chemically with the color component does not affect the light absorption as a rule. However, large amount of electrolyte may affect the absorption spectrum quantitatively as well as qualitatively. This is due to the physical interaction between the ions of the electrolyte and the colored ion on the molecule. So due to the interaction between the colorless ions of the electrolyte with the molecules, so there will be chance of positive or negative deviation. This interaction results in a deformation of the curve, thereby causing change in the light absorption, property. And another cause of deviation, that is hydrogen ion concentration. There are a number of substances whose ionic state in the solution is greatly influenced by presence of hydrogen ions. For example, aqueous solution of potassium dichromate involve the chromate ion, dichromate ion as in equilibrium this. So here the chromate ion and dichromate ion is in equilibrium due to presence of hydrogen ion. The chromate ion has a lambda max value 375 nanometer, while the dichromate ion has two lambda max values, one at 350 nanometer and another at 450 nanometer. The position of the equilibrium depends upon the pH of the solution, and the yellow color of the solution changes to orange color with increasing the concentration of hydrogen ion. That means if the solution will become acidic, that will changes into orange color. That means increasing concentration of the H plus ion, the solution becomes orange color. Therefore, the results of determination of the chromate ion concentration will depend upon the pH. Thus, it is imperative that the substances whose color is influenced by the change in hydrogen ion in concentration must be studied under the condition of same pH. In some cases, do two observing species are in equilibrium have a common value of observability at a certain wavelength. For example, in case of bromothylal blue, the absorption spectra at different pH values are different. However, a wavelength of 501 nanometer, as you will see, all the species have the same molar absorptivity. So this is the absorption spectra of bromothylal blue. So that is one type of dye. This is absorption spectra of bromothylal blue. That is one a type of dye. So that is showing at different pH values, showing isoelectric point at 501 nanometer. So here at 501 nanometer, at wavelength of 501 nanometer, we see all the species have same molar absorptivity. Therefore, no matter to what extent does one species change into another, there is no change in total absorption. Such wavelength is called isobestic point. So at this wavelength, the Beer's law holds good. At other point, the Beer's law does not hold good. Now coming to complexation, association or dissociation. So these are also some causes due to deviation of the Lambert's-Beer's law. Some salts have a tendency to form complexes whose colors are different from those of the simple compounds. For example, color of cobalt chromate, color of cobalt chloride changes from pink to blue due to following complex formation. So this is cobalt chloride. So initially the color of the cobalt chloride is pink color, and that will changes into blue color due to formation of this complex inside the solution. The degree of complex formation increases with increase in concentration. Therefore, the Beer's law does not hold good at high concentration. Now, another cause of deviation of Beer's law, that is non-monochromatic nature of the radiation. So, the Beer's law hold good if it is necessary that monochromatic light is used. However, most spectrophotometer and all filter photometer discussed later, so that will discuss later. So that is due to non-monochromatic nature of the radiation, a wider bandwidth of the radiation will be possible. Now coming to concentration of analyte. As per the Beer's and Lambert's law, the plot of the observance versus the concentration of the observing substance would be a straight line when epsilon and beta are constant. The path length can always be held constant, but there are some factors which affect the epsilon, and it is found that at high concentration epsilon is not constant. Therefore, at high concentration there may be deviation from the law. Now coming to temperature. The temperature is not considered an important factor since ordinarily the measurement is made at constant temperature. However, changes in temperature sometimes may shift the ionic equilibrium and thereby change in the absorptivity. For example, color of acidic perchloride solution changes from yellow to reddish brown color on heating due to change in the lambda max value and change in the absorptivity value. So that means when temperature will change, there will be deviation in the Lambert's-Beer's law. Now coming to the instrumentation for the UV visible spectrometry. So the five essential component of the UV visible instrument are as follows. So the first one is a stable radiation source. The next one is wavelength selector. Third one, sample holder. Then next, radiation detector or transducer. And the final one is signal processing and output device. So here that is the radiation source. Then monochromator. Monochromator means wavelength selector. Then the sample cell compartment that containing the sample. And after passing of the monochromatic radiation through the sample, the detector will detect the monochromatic radiation, that means change in any type of intensity or wavelength of the monochromatic radiation, and after that will give the output signal. So here we will discuss one by one. The first one is radiation source, that is source of UV region. For the measurement of UV region, dielectric discharge source, electric discharge source like hydrogen or deuterium lamp are used. So these are the source of light, or these are the source of electromagnetic radiation in the UV region, that is hydrogen or deuterium lamp. In these, the excitation of the gaseous molecule is brought about by passage of electrons through the gas at low pressure. A hydrogen lamp is commonly used for the spectrophotometer and gives the light of wavelength region within 160 to 375 nanometer. Now the source of visible region. So for visible light, the source is the modern instrument use a tungsten filament lamp. So for hydrogen lamp is used for UV light, and hydrogen or deuterium lamp is used for UV light, and a tungsten lamp is used for electromagnetic radiation of visible region. So that is having and it gives electromagnetic radiation of wavelength range 350 to 2200 nanometer. Now coming to the wavelength selector. So the wavelength selector, that means that is the monochromator. So here the monochromator, that is first one is absorption filter. In low cost instrument to measuring the visible range, colored glass filters are used to cut off the undesirable wavelength. A typical filter in a colored piece of glass which absorb light of certain wavelength and allow that other parts to through it. You know that when the white light is made to fall on the nickel prism, so that will split into different colors, that is vapor, that is for violet, indigo, blue, green, yellow, orange and red color. These seven color add up to give the white color. When the light when white light falls on an object, a part of it is absorbed and the rest is transmitted. These transmitted components add up to give the observed color to the object, and the observed component and the observed color can be again add up to give the white light. So these are therefore complementary to each other, and the object particularly color looks that the object. So if any object absorb one color, that will looks like its complementary color. So the complementary color you can see from this color wheel. So that means, so this is the color wheel. If any substance will absorb red color, that will looks like green. Any substance will absorb yellow color, that will looks like violet. Any substance which will absorb orange color, that will looks like blue. So this is the color wheel. Now coming to monochromator. So the first one is, so monochromator. A monochromator is the devices that can selectively provide radiation of a desired wavelength out of the range of wavelength emitted by the source. Because from the source, a range of from the source, electromagnetic radiation of a particular range will come, and when that will pass through the monochromator, so that will change into electromagnetic radiation of a particular wavelength. So there are so these are two types. The monochromators are two types. The first one is prism monochromator, and the second one is grating monochromator. So these are the diagrams, that is diagrams and mechanism showing how the prism monochromators will change the polychromatic light into monochromatic light, and this is the grating monochromator that will change into polychromatic to into monochromatic light. Now coming to the sample handling. For the UV visible absorption spectra usually determined either in the vapor phase or in the solution phase. In order to take the UV spectrum of the annulate, that is taken in a cell, that is called cuvette, which is a transparent to the wavelength of light passing through it. A variety of quartz cuvettes are available for the spectral determination of the vapor phase. These are varying path. So these are the cuvettes used for the spectral measurement. So these are the quartz cuvettes for the measurement of solution, are for the measurement in for the measurements in solution and in vapor phase. Now coming to the detectors. So the after when monochromatic light of wavelength in the UV or visible range will pass, After passing through the sample, the light will be detected through the detector. So different types of detectors are there. So the first one is photo tube detector. The second one is PMT, that is called photo multiplier tube, and the third one is diode array detector, and the fourth one is signal processing, and the next. So these are the three different types of detectors. First one is photo tube, the second one is PMT, that is photo multiplier tube, and the third one is diode array detector. And then after that, signal processing and output device. So the electrical signal from the transducer is suitably amplified and processed before it is sent in the recorder to give an output. The subtraction of the solvent spectrum from the solution is done electronically. That means initially you have to analyze the solvent, only solvent through the UV visible spectrophotometer, and that will give a particular spectra. And after that, you have to add the sample means annulate within that solvent, that will form a solution. And when we will measure the UV visible spectra of the solution, so that will electronically subtract the UV visible spectra of the solvent. So that means that will give the UV visible spectra of the only the observing species. Now coming to the type of instruments, the first one is single beam spectrophotometer. So this is the single beam spectrometer, and the next one is double beam spectrometer. You can see for the single beam spectrometer, only one type of wavelength or only one wavelength will pass through the sample and reference. And for the double beam spectrometer, so there so monochromatic two monochromatic radiations will pass inside the sample. Two monochromatic radiation will pass inside the spectrometer. One will pass through the sample and another will pass through the reference. And after that, at the amplifier, the change in the wavelength will be measured. Now coming to the analytical applications of the UV visible spectrometry. The first one is qualitative application. So for qualitative application, and the second one is quantitative application. You can see in terms of qualitative analysis of the analyte, the UV visible spectrometry is of a secondary importance for the identification and the determination of the structural details. The information obtained from it needs to be supplemented by the, so you cannot analyze any sample through the UV visible spectrometer only. So it should be supplemented by that of the IR and NMR, IR or NMR or mass spectrometry. So that's why that will give the complete characteristics of the analyte. This is because the sample and the broad nature of the spectra. So generally in the UV visible spectrometry, in the solution phase, that will give the broad spectra. So in order to find the complete characteristics, the UV visible spectra should be supplemented by IR or NMR or mass spectrum. Now quantitative application. So in the quantitative application, we can determine analytical determination of metal or non-metal present in the sample, analytical determination of organic compounds, now determination of dissociation constant of organic acids or dyes, determination of metal ligand formation constants, determination of kinetic stability of the complexes. So these are quantitative analysis, and these are the quantitative analysis methodology. So you can see, so during the quantitative analysis, first you have to do the calibration curve. So in the calibration curve, you have to take the standard solution, and after getting a standard solution, the sample to be analyzed. Suppose one unknown, uh, um, suppose one unknown concentration sample is there. In order to know the concentration of the sample, first you have to take known concentration of the same sample with different concentrations. So here 5 known concentration of the same samples are there, and that will give particular absorption observance. And after drawing the curve of concentration versus absorbance. So that will give a straight line, and after that, if we put the solution of unknown concentration, that will give a particular observance, and from that particular observance you have to draw a normal from the core, and finally you have to determine the concentration of the unknown sample. So here one example is there, that we will go through the example, and here after that we will discuss the next one. The next one is the infrared spectrometry. So here we will discuss the infrared spectrometry, the next chapter. Now we will discuss the theory of infrared spectrometry. The bond between the two atoms in a molecule is not rigid, that we know that. So when two atoms will undergo a formation of bond to form a molecule, so the bond between the two atoms is not rigid. It has elasticity, and as a consequence, the atom of the molecule do not remain fixed in their position. They are in a constant state of motion around their main position. The molecule is said to be undergoing vibrational motion. The quantum mechanical treatment of the molecular vibration motion shows that it is quantized. As the transition between these quantized energy levels can be brought about using electromagnetic radiation in the IR region, it will give the IR spectrum. as the excitation as the excitation among the quantized vibrational energy levels of the molecule is involved, the IR spectroscopy is also known as vibrational spectroscopy. That means when electromagnetic radiations within infrared region will fall on the sample, then the sample will undergo bond vibration. So due to this bond vibration, the so there will be change in the vibrational energy levels of the sample, and that will give rise to IR spectroscopy or vibrational spectroscopy. So first we will discuss the vibration of a diatomic molecule. So initially we will consider a simple diatomic molecule. So diatomic molecules means the two atom. So there will be a bond between two atoms to form a molecule, and let the diatomic molecule is AB. So the bond between the diatomic molecule AB can be visualized as a simple harmonic oscillator, as shown in this figure. So this is let the atom A, and this is atom B, and the distance between the atom A, and so the equilibrium distance between the atom A and atom B is known as Req. So the bond length, that is Req, is the equilibrium distance between the two atoms A and B to form the molecule. And here the bond, so here the position of the two atoms are not fixed. So there will be expansion and compression. So the position of the atom A will undergo expansion and vibration like this, expansion and compression like this. So that means there will be a regular change in bond length of the diatomic molecule AB. There may be the equilibrium distance, so the bond length may be less than the equilibrium distance for compression, and there will be more than the equilibrium distance Req for expansion. So the quantized energy levels obtained by the quantum mechanical treatment of the harmonic oscillator, so that is given below. So this is for the harmonic oscillator. So you can see, so this is the equilibrium distance Req. So there is a chance of compression and expansion. For compression, the bond length will decrease for Req, and for expansion, the bond length will increase. And so that means when electromagnetic radiation of infrared region will fall on the diatomic molecule, the bond between the two atoms will undergo vibration. This is the Req, equilibrium distance between the two atoms. When that will undergo vibration, that will undergo compression or expansion. And similarly, when the energy of the electromagnetic radiation again increase, the extent of compression and expansion will also increase. And That's why that will give rise to this type of parabolic curve. So this is called simple harmonic oscillator. So the two atoms, so these are the equilibrium position between the two atoms. When the IR, when electromagnetic radiation of IR so region will fall on the sample, that will undergo expansion like this, or that will undergo compression. That means, according to that, the molecule will never dissociate. But in actual case, when more and more energy will be supplied just to increase the amplitude of the vibration, so then at some highest energy state, the molecule will undergo break, or the bond will undergo break. So the bond will break. When the bond will break, the two atoms will be separated, and that will give rise to atomic spectra. So here we are discussing about the molecular spectra. So in the actual case, the diatomic molecule will behave as anharmonic oscillator. So this is the diagram for the anharmonic oscillator, and this is the optimal energy. So that means when this much amount of maximum energy will be supplied, the bond between spectra of the molecule, because the molecule AB will be converted into two isolated atoms A and B. So here today we will stop here, and tomorrow again we will continue from this. Hello. So today we will stop here, and tomorrow again we will continue. Hello. Hello.
जी सर.
Okay.